Hi everybody, I am Arturo Pascuzzo and I'm from University of Calabria in Italy. The work that I'm going to present deals with crack propagation analysis in masonry structures via an inter-element cohesive fracture approach. In particular, the work proposes a comprehensive investigation on the assessment of mesh density issues that can affect the accuracy and the numerical stability of cohesive modeling strategies. This work is co-authored with Fabrizio Greco, Lorenzo Leonetti, Paolo Lonetti, and Camilla Ronchei from University of Calabria. During the last years, the assessment of modern or historical masonry structures using numerical simulations has become a topic of great interest. In the framework of computational fracture mechanics, it is well known that a reliable assessment of masonry structures require a proper definition of all the sets of fracture mechanisms occurring at the microscale, the scale in which masonry can be viewed as a combination of unit and mortar joints. At the microscale, according to the arrangement of units and mortar joint, we then distinguish between regular or irregular masonry. The mechanical properties of unit and mortar joint and their arrangement strongly influence the typology of fracture mechanism. Essentially, we can define four types of fracture mechanism, which are micro-crack nucleation and propagation within mortar joints, the bonding along unit-mortar interfaces, fractional static contact between opposite crack faces, rocking of indented crack edges. Effective numerical strategies should be able to account for all these mechanisms regardless of the geometric configuration of the masonry. A detailed micromodeling approach represents an effective strategy to obtain an accurate prediction of fracture behavior of masonry structures. Detailed micromodels are based on a refined representation of the geometry of the masonry. In this framework, the mortar cracking is reproduced by means of a nonlinear material model based on damage causative laws. In addition, interface elements are placed along brick mortar interfaces to reproduce the bonding phenomena. These strategies present many advantages. By contrast, it is computationally expensive, and it is not able to capture the discrete nature of mortar cracking. Recently, diffuse cohesive volumetric finite element detailed micromodeling approach has emerged as a valid alternative. This modeling approach consists of the insertion of cohesive interface elements along all the internal boundaries of the given volumetric finite element mesh. In particular, with reference to masonry, interface elements should be inserted along the boundaries of mortar bulk. This strategy captures diffuse cracking mechanism in a more natural manner. However, such an approach can undergo difficulties to simulate tensile cracking phenomena. In fact, the possibility that many cohesive elements will manifest simultaneous softening behavior can lead to convergence issues. The key consequence is the occurrence of multiple solutions without any physical sense. In addition, the presence of multiple interfaces with finite stiffness can engulf thin mesh dependency issues because an unavoidable induced compliance effect. As a consequence, contributions to address such issues are currently much required to increase the reliability of diffuse interface modeling approach. On the basis of the previous consideration, with this work our objective was to develop an effective strategies to address the convergence issues that affect the diffuse interface modeling approach when multiple interfaces undergo softening behavior under tensile action. The proposed strategies is presented by considering the direct tensile test of a brick masonry couplets. However, it is quite general to be applied to other cases involving tensile softening behavior. The presentation is organized as follows. In Italy, there is a theoretical background section where we report the variational formulation for the adopted cohesive volumetric finite element approach, followed by a review of the loss of uniqueness and stability issues which typically affect the diffuse interface modeling approaches. Subsequently, we propose our strategy to overcome such a drawback. Part 2 provides numerical implementation details. In Part 3, we propose numerical results. In particular, failure mechanisms occurring along brick mortar interfaces and within mortar joints are investigated separately. Finally, the main conclusions of the work are discussed. To introduce the cohesive volumetric finite element approach, let us consider a generic two-dimensional domain in which four node interface elements are placed along every boundary of the mesh. Under the hypothesis of quasi-static loading, small deformation, and linear elastic behavior of bulk elements, The mechanical response up to the failure of the materials is obtained by solving a nonlinear boundary value problem expressed by the following V formulation, in which interface element contribution is marked in red. This contribution depends on the interface element formulation. In the proposed model, the interface model consists of a mixed-mode traction separation cohesive law incorporating a nonlinear softering response. The damage variable is defined by means of a linear exponential damage evolution law, which provides a better representation of the fracture mechanism occurring in quasi-bitter materials. The damage variable depends on the mixed-mode displacements at damage initiation and complete decohesion, which are defined on the basis of proper damage initiation and complete decohesion criteria. In the diffuse cohesive finite element approach, the presence of multiple interface elements that undergo softening behavior simultaneously may lead to the occurrence of bifurcation and localization instabilities. To highlight the problem, let's consider an example of discrete nonlinear mechanical system made of equal linear elastic bulk elements and zero thickness interface elements alternately arranged and subjected to a tensile force under increasing controlled displacement conditions. This problem can be solved by applying a classic energetic approach. So, by writing the total energy of the system, we can see that it depends on the elongation of the bulk interface elements, as well as a parameter, denoted as alpha, that describes the damage status of each interface. Now, let's simplify the problem by considering its homogenized counterpart. In this way, the total energy expression simplifies, so thus depending only on the damage variables. The equilibrium problem can be now solved by minimizing the strain energy with respect to the damage variables according to the well-known Karush-Kuhn-Tucker conditions. Two distinct cases can be defined. By considering the critical value of the imposed elongation as a reference, displacements less than this value identify stable solutions, in which interfaces are completely undamaged. For larger displacements, in which the damage parameter is not zero, the mechanical problem loses its uniqueness, and multiple global or local stable equilibrium solutions occur. Such solutions are characterized by distinct mechanical configuration in which different damage patterns are allowed. By excluding the effective solution, marked in magenta, the remaining ones lead to anchored prediction of fracture patterns and fracture energy. For this reason, such solutions have not physical sense. To avoid the occurrence of multiple stable or metastable equilibrium states, a possible solution relies on the introduction of some form of imperfection in terms of material variability. This can be done, for instance, by considering a random spatial distribution of the cohesive strength values assumed for the embedded interface elements. This determines a sliding form of heterogeneity in the numerical model. So, cohesive strength values are implemented in the numerical model using a Weibull distribution. This ensures that only a unique interface will present the minimal strength value, thus avoiding simultaneous damage initiation in more than one interface. Both tensile strength and cohesion value of each interface are modified using an imperfection function, which depends on the Weibull modulus and a function eta that generates a weight and noise uniform spatial distribution of values ranging between 0 and 1. Here, there are some examples of a function eta for one-dimensional problems by assuming a Weibull modulus of 10. For two-dimensional cases, the imperfection functions consist of a surface of variable values. Since the values generated by the imperfection functions possess a continuously random character, abrupt change of strength within the same interface elements can occur, thus leading to numerical convergence issues. To avoid such a drawback, the imperfection values corresponding to the centroid of the element is assigned to the entire interface element. To assess the efficiency of the proposed strategy, we consider a masonry couplets commonly used for direct tensile tests. In particular, we assume undamageable units so that fracture can originate along pre-mortuary interfaces or within the mortar joint. Because of the symmetry of the scheme, only half of the masonry sample is implemented. The cohesive volumetric final mesh is constructed by using an automated procedure that consists of the following 4 steps. Once that the mesh is constructed, the cohesive stiffness must be properly calibrated to reduce the invaluable compliance effects. The calibration strategy is based on the following dimensional parameters that permits obtaining the proper cohesive stiffness values. We adopt these values of dimensional parameters, which ensure nearly invisible interface elements. Firstly, we analyze the fracture of the masonry sample because of the brick-mortar interface creases. To this end, the numerical model comprises cohesive elements placed only along the brick-mortar internal boundaries, assuming the mortar joint as elastic. We consider the diffuse numerical model and 2 auxiliary single interface models reproducing the stable and metastable solution respectively. So, first we compare the results of the diffuse model without imperfection with the prediction of the auxiliary models. By observing the stress elongation curves, the proposed diffuse model suffers from unique issues after the peak stress, because the softening branch follows that predicted by the metastable auxiliary model. At a certain elongation, the diffuse model leaves the metastable equilibrium path, and it follows a secondary and more stable branch which tends to the stable equilibrium solution. Now, we introduce numerical imperfection in the model and repeat the analysis for different values of the value parameter. It can be seen that our strategy avoids the occurrence of metastable solution. Now, we investigate the damage of the couplets due to the failure of the mortar joint. The brick-mortar interfaces are assumed to be undamageable in this case. The results of the proposed diffuse interface model are compared with the prediction of an auxiliary single interface model involving a single layer of cohesive elements placed along the middle plane of the mortar joint. Firstly, we consider 3 sets of regular meshes for the mortar joint, which differ to each other depending on the size of the elements. Without imperfections, the results show that the diffuse model with the coarser mesh suffers from instability issues in the steps soon after the tensile peak because of the simultaneous damage, nucleation and propagation in the 2 horizontal interfaces embedded in the mortar joint. By using the other meshes, we observe a more stable solution close to that obtained by the single interface model. However, a little deviation with respect to the stable solution involving crack localization is observed. By considering numerical imperfection in the numerical models, the solutions are comparable and close to the stable one, even though different crack paths are observed. The same case is now investigated by using more general unstructured meshes of different sizes for the mortar joint. The results show that the use of unstructured meshes avoids the occurrence of metastable solutions. This is because the irregularity of the element distribution serves as an intrinsic source of diffuse imperfection. However, to analyze the effect of the imperfection when using unstructured meshes, we select the most refined mesh, which is here named as D3, and we analyze the response of the couplet adopting 3 distinct random seeds. The result showed that the introduction of the cohesive strain imperfection has no sensible influence on the predicted loading curves. However, different final crack paths are observed. In conclusion, in this work we have presented an effective detailed micromodel based on a diffuse interface modeling approach for the analysis of tensile cracking behavior of masonry structures. The proposed model adopts a proper strategy to avoid the occurrence of bifurcation instabilities that may affect the global softening response, mainly due to the simultaneous opening of adjacent parallel interfaces when subjected to a uniform stress state. The proposed strategies consist of introducing small random fluctuations in the cohesive strength of the bend interfaces according to a given weighable distribution. So the probability that multiple interfaces reach the minimum strength value within the same embedded packages is reduced, thus ensuring the uniqueness of the numerical solution. Comparison with simplified micromodels reproducing stable solutions for the standard fraction mechanism occurring at the micromortar interfaces or within the mortar joints have shown that the proposed strategy is really effective, thus providing reliable numerical prediction. Thank you for your attention.